Okay, hey everybody. I got the feedback that the material at the end of the last lecture on queues went a little fast, and so I just want to quickly go over the slides again. We talked about queues being a line, right? So the British definition is a line, and we use this analogy of going to McDonald's and you get in line, and the first person who gets in line is the first person who's called to the front. And so when we're talking about queues, we're talking about just the data structure that is a line. And so we said this was a first in, first out data structure where stack is the last in is the first out. So with a stack, you place a stack tray and another tray and another tray, and then if you're going to pull a tray off, you pull out the last one in. Last in is first out, and with queue, you have the first person in line, second person in line, third person in line, and when you call someone, you call that first person, and then the next person called is the second person, and so on. And so queue is first in, first out. The methods, so for all of our data structures, we need an initialize method, and then the other methods are enqueue to enter the queue, you get in line, and dequeue, exit the queue, you get called out of the line to order at McDonald's. And then we also said that there was a method called front, and the idea with front is that you can just look to see if there's somebody in the queue, and you'll need this for 3C. And so this would be analogous to if you're working the register at McDonald's and you want to know if someone's in line, you look up and you see, and then if there's someone there, you might call DQ to pull them out, or maybe you'll do some other stuff, but you can just see if there's someone at the front of the line. And so here was first pass at the implementation. And I think as we discussed it, I know we discussed this for a while, maybe it was with stacks, but this is just defining that when we have max elements that it just resolves to 10. We talked about the compiler preprocessor and that it would just substitute every max elements to be 10, and it was that just making a variable like a global int max elements equals 10 was problematic for the compiler, and this is kind of the preferred way of doing it. And then here's our struct, and so our struct has a data member where it says num elements, and perhaps a better name for this one would be like count or number in queue right now, or something like that. And then this is a queue, or what it's storing are ints. And if we wanted to do a queue with it stored people, then I guess the type here would be like customer or something like that. And so the maximum number is the number of elements. So when we initialize, we set this data member num elements to be 0. And again, if it was a different name like number of people in line, then that'd be setting that to 0. And the big thing is for this enqueue, that, well, first off, we have a maximum number, and so maybe that only 10 people can stand in line. And if there's 10 people in line, you try to add someone else, then you have an error condition. And otherwise, you copy over to this new value, and again, this type matches that type. And if we were instead doing customers, then this would be customer, and that would be customer, and we set this customer to whatever the current position is in line. So at the beginning, when the number of elements is 0, then we set them at position 0, and then we increment this and it becomes 1, and the next time we put the next value at position 1 and 2, and so on. And so here's a slide showing enqueue in action, and this is just the same enqueue method, so you can look at it. As we call this and reason about what we're seeing as the values of things, and so here we call initialize, and then we call enqueue a bunch of times. And so one of the arguments to enqueue is the queue, and so here we've made a queue on the stack, and we pass in the address of the queue, and then we enqueue 4 different numbers, 10, -5, 14, and 8, and as we do, they get placed at elements 0, 1, 2, and 3, and then there's the values 10, -5, 14, and 8, and the number of elements increments each time. When we dequeue, so this was the wrong dequeue, or not wrong, but it was the dequeue that had O of n complexity. And so you probably recall in class that we got everybody, or not everybody, the front row up on stage, and we did this thing where we dequeued the first person, then we made everyone else scoot forward one, and that was O of n complexity, and this represents that O of n complexity. And so then the trick where we can make it be O of 1 is later in the slides. Here's our same NQ, but now we're doing DQ, and you can see there's the implementation for DQ. And when we call DQ, the first thing we get is 10 because that's the first thing we put in, first in, first out. When we do DQ again, we get minus 5. So the first one in was 10, the next one was minus 5, so we get minus 5. And when we do this, the number of elements is shrinking from 4 to 3 to 2. And then what's in elements is getting copied over. So it's 14 and minus 8. And you see I have this dot, 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 meaning we don't care what's past there. We actually had a question during class of, well, wait, what is past there? And I think the way it's implemented, the next one would be minus 8 as well, and the one after that would probably be minus 8 because we're just copying things down one. But at the same time, it's a minus 8, but we don't treat that as valid. When the number of elements is 2, we only treat element 0 and element 1 as valid, and whatever's past that is whatever. So then we had this observation about the time complexity. O of 1 for NQ, O of n for DQ, and we asked, can we do better? And that's when I was, you recall when people got to the front and I was working the register, that instead of calling people to the register and having everyone scoot forward one in line, I started walking to the people, and that made it be O of 1 work. And so then the way to do this is to have two separate pointers, a front and a back. And if they're not, I said pointers. Let me say pointers is the wrong word because I actually don't mean pointers here. To have two separate indices, trackers. I don't want to say pointers. Front and back. And so front is for the next element to be DQ'd, and back is where your next NQ should write to. And if they're equal, that means there's nothing in the queue. And so now, if we do an NQ of 10, well, we start with front and back pointing to index 0. And if we do an NQ of 10, then back goes to index 1. And back is pointing to, when you do another NQ, where should you put it? And front is pointing to, when you do a DQ, what should you pull out? And so if you do an NQ of 10, well, front is pointing at this 10 because that's the next thing to pull out, and back should point at the next index. And then if we did another NQ, then we put in a minus 5, and back goes forward 1, and so on, and so on. And then when we do a DQ, front, we DQ'd, and that would return 10. And then front moves forward because the next one we return is minus 5. So this is exactly like when I stood in the front of the classroom and I was the McDonald's employee and I walked to the next person in line, and whoever I took the order from, maybe they walked off, maybe they didn't, I don't care. And so this still says 10 in there. So what? It's not part of what we're tracking. We're only tracking now the minus 5, 14, and minus 8. And if we keep NQing and back goes further and further and further and further, and here, and we overwrite the 10, so what? We're done with it, and we've already returned it in this DQ. Now, where we'd get into trouble is if we're doing NQs and back goes there and there and there and there and there and there, and then it walks into front. So you don't want it to be that as you're NQing, back walks into front, because that means you've got, in this case, there's only 10 spots in line. It would mean that you're using more than 10 spots. And so there's an example of a DQ, and doing another DQ, and we leave minus 5 there. And the time complexity now for the DQ is gone to O of 1. And so the comment here is now you have to manage 2 locations and you have to deal with wraparounds. And so then the project 3C project is you need to implement queues, the O of 1 kind, and it's solving a specific problem, which is matching up surgeries between donors, recipients, and hospitals. And I think there's already a video on that. So I'm going to stop here because I just wanted to, and this is, I think, just as fast as when I said it in class, but hopefully now people can at least pause and rewind it and get more out of it. So if stuff isn't clear, let me know. I can film more videos, or we can add comments to this video. Okay, good luck everyone.